you are doing well today. Today we're going to be starting a new chapter, and this chapter is about rational functions. And one of the first types of rational functions, and we'll get into more of that in 9.3, but is inverse variation. And I don't know if that word reminds you of anything. It kind of should. So I put here, recall that we have done another type of variation. We have done a type of variation called direct variation. Back in chapter 2, it was a long time ago, I know, but we had direct variation, and the equation of direct variation was this: y equals kx. It was linear, of course, and so we basically, another way of saying it, it was also called direct variation, is also called proportional. So also we would call it direct proportionality. So, and that comes from this guy right here. If I were to write this as a proportion and solve it, you would get y times 1 is y equals, well, kx. K was the constant of proportionality, or we would call it sometimes the constant of variation. But again, K, which is that constant, was equivalent to the ratio between y and x. It was y over x. And that is important because today we're going to be talking about inverse variation. It's a little bit different. In inverse variation, the inverse of multiplication is division, so that kind of should make some sense, because when you look at this, you're multiplying k and x. But when you look at inverse variation, the formula that we're going to use is y equals k divided by x, not k times x. And again, if we were trying to solve for k, we would multiply both sides by x, and you would get the constant k is equal to y times x, or x times y. That's pretty important. I'm going to bring up here on the board when you have direct variation by contrast. When you have direct variation, you have y equals k times x, and the constant is equal to y divided by x. That's for direct variation. In inverse variation, you have y equals, I'll just kind of get rid of this guy here. You have y equals k divided by x. And the k value is x times y. So it is different from direct variation. So I want to show you an example of how we can find a formula for direct variation. And it says here, suppose that x and y vary inversely, and x equals 3 and y equals negative 5. Write the function that models the inverse variation. This is a very simple process. You need a function. When it says write the function, it's looking for a function like this, y equals k divided by x. And the only thing that we're really missing is we don't know what k is. We don't know what the constant is. And that's why it's important to look at it in this way as well. In the end, we have to write the function in this form. But to solve for k, all we have to do is find the y value and the x value and multiply them. So we know that x equals 3 and that y equals negative 5. So k will equal negative 5 times 3, which is actually negative 15. And then you just plug k into the function model, and you get that the function would be y equals negative 15 over x. And that is how complicated that example is. All right, so this will be my final answer. So I would like for you to try this example here. And then we'll move on to something that's a little bit more interesting, I guess. And example 2 says, is the relationship between the variables in each table, so we have 3 tables here, is it a direct variation? And again, I want to remind you that direct variation would be y equals kx, and the constant for direct variation would equal y divided by x. Kind of write small there, y divided by x. It's asking us if the relationship is a direct variation or is it an inverse variation. And in the inverse variation case, the constant is equal to x times y or y times x, either way. So basically in direct variation, it's a ratio of y and x. And an inverse variation is the product of y and x. Or is it neither? Okay? So the way that we do that is we look at each of these tables, and if you recall from before, in order for it to be direct variation, the constant has to be the same for all of the values. So what I'm going to do is just very quickly check those values, and it's not really hard to do. You can do it very quickly with a calculator. And I'm going to say that if it's going to be direct variation, it's going to have to be k equals y over x. So I have to take 1.5 and divide it by 0.5. I have to take 6 and divide it by 2, take 18 and divide it by 6. And every time I do that, I should get the same value. So 1.5 divided by 0.5 is 3. 6 divided by 2 is 3. So far, so good. And of course, 18 divided by 6 is also 3. So in this case, when I did the ratio y to x, I always got the same k value. So this is direct variation. And if you don't believe me, you could try the inverse variation. You could multiply x and y, 0.5 times 1.5, and you get 0.75. So if I were multiplying these, I get 0.75. And if I take 2 times 6, that's 12. And 6 times 18 is 108. And very quickly you can see that when I multiplied the x and y values, I did not get the same k. Therefore, it is not inverse variation. And because I divided the y and x in this way, I always got 3, then that means that this particular table is a model of a direct variation. Notice also that the directions say once you've decided whether it's direct, inverse, or neither, it's asking us to write the function that models that situation, whether it be direct or inverse. Okay, if it's neither, then we don't do anything. So in this case, we found that we got the same k value, and so you remember that direct variation is y equals k, which in this case is 3x. So this would be our model for part A. So in part B, we do the same thing. We try to see if it's direct variation. So I take 12 and divide it by 0.2, take 4 and divide it by 0.6, and take 2 and divide it by 1.2. And 12 divided by 0.2 is 60. And 4 divided by 0.6 is not 60, it's 6.6 repeating. And at that point, there's really no need for me to keep going. If these aren't the same, then it's not direct variation. So then I want to try the inverse variation. So I do 0.2 times 12, 0.6 times 4, and 1.2 times 2. And 0.2 times 12 is going to equal 2.4. 0.6 divided by 4 is 0.15. And again, we're seeing, I'm sorry, I divided, not multiplied. 0.6 times 4 is also 2.4. So far, so good. And then 1.2 times 2 is also 2.4. So in this case, we got the same k value by multiplying. So in this case, it's going to be an inverse variation. And the equation for an inverse variation is y equals k, which in this case is 2.4, divided by x. 2.4 there. Looks kind of weird. But that would be my answer for part B. Y equals 2.4 divided by x. And then we go to our last example, and we try the direct variation. So in that case, we're going to try to go 2 divided by 1 is 2. 1 divided by 2, however, is 0.5. And already we can see that we're not going to get the same k value, so it's not going to be direct variation. So then I want to try inverse variation, and I say 1 times 2 is 2. 2 times 1 is 2, so far so good. But then 3 times 0.5 is not 2. 3 times 0.5 is 1.5. And so just because 2 of them work doesn't really matter. If all of them don't work, it doesn't count. So it's not direct variation. It's not inverse variation. So in this case, we say it's a big fat neither. And if it's neither, then we don't have to write the model because there isn't one. Okay? So that's how you can determine what type of relationship it is. And so now you can try this guy. And then we'll move on to the next item of business with inverse variation, and that's combined variations. So we've talked about direct variation, we've talked about inverse variation, and you can also do a combined variation where you put inverse variation and direct variation together in the same problem. I know it sounds scary, right? But it's actually not that bad. I'm going to give you some examples real quick of how easy it is to do a combined variation. Keeping in mind that whenever you have a variation at all, whether it's direct or inverse or joint variation, you always want to have a constant, which we'll just keep calling k in this case. So when I read the first example, these are, by the way, these are like 1, 2, 3, 4, 5 examples here. We have y varies directly with the square of x. So the way that would look as a formula is that y, and because it varies directly, whether, again, what I said was if it varies whether directly or inversely or jointly, doesn't matter what kind of variation, you always need a k. So direct variation, remember, is like y equals kx, but this time it's not, it doesn't vary directly with x, it varies directly with the square of x. So that would be x squared. And that's it. So this guy right here, the formula or the equation for it would be y equals kx squared. So I'll do another one. Now we're going to do all of these. And hopefully, you can start catching on. Y varies inversely, and since it's inversely, we're going to put the k on top and then the variable on the bottom, and it's the cube of x. So that would be x cubed. And that's that. Then we have a joint variation, which means we're going to have two variables. So we have z this time. So z varies jointly, and again, whenever you have any type of variation, you need a k, a constant. It varies jointly with x and y. So there we go. We just put both variables there, kx, y. So now you have that guy. Here we have z again, varies jointly, I forgot a word there, I should say, with x and y, but also inversely with w. So because it has an inverse and a direct, you're still going to need a division bar here, but jointly with x and y, so we're going to put our k up here, x and y, and inversely with w, so the w is going to go on the bottom. So the direct variation is the x and y, it's on top, and the inverse variation, which is with the w, is on the bottom. And that's how you do that guy. And then we have our last one here. Z varies directly with x, so we're going to have kx, and inversely, so we have our division bar, with the product of w and y. Well, that's w and y, and they're being multiplied. And that's how you would get the equations for those different, sorry, my phone is ringing. Sorry for that interruption. But anyway, so that is how you get the different equations. And so now we're going to try this in our homework or in our examples here, how to combine this variation stuff. Basically, you're going to be asked to either describe this formula using the words that we've I'll say, wow, okay, calm down, Ms. Martinez. Let's say this correctly. Basically, if I go back to this is like a verbal description, if you will. This is the algebraic description of the variation. So the next two examples that we're going to do, this first example is for us to describe this using a verbal description. And then the next example, we'll go backwards and try to extract the equation from the verbal description. All right, so here we go. Newton's law, and don't get scared, it's a pretty long problem, but don't get scared. Newton's law of universal gravitation is modeled by the formula, and you have it there in green. And now it's just going to describe to us what all those variables actually mean. F is the gravitational force between two objects. So you've got two objects, and they each have their own gravitational force. And F is the force, sorry, they each have their own mass. And F is the gravitational force between the two objects. M1, F sub 1, and F sub 2, which are these numbers right here, those are just representing the mass of each object. D, which is on the bottom, is the distance between the objects. And of course, G is the gravitational constant, and that's actually pretty important because normally we use K for our constant, but in this case it's telling us that G is the gravitational constant, so we're going to use G as our K value. So they want us to describe Newton's law as a combined variation. So basically what we're saying here, in a nutshell, is that when you look at this, you're saying because the M1 and the M2 are on top, that's going to be direct variation, and because the D's on the bottom, that's going to be inverse variation. So all we really have to do is say that in words, okay? So we could say that F varies directly with M1 and M2, but we could probably tell them what, because we know what M is, we can be more specific and say that it varies, and we don't want to say directly. Sorry, I did one little thing that I do want to add here. I don't know if you picked up on it, but we should say jointly because we have two variables. So so this is a direct variation. So we're going to go F varies jointly with, and what do the M stand for? They are masses. So with the masses, M1 and M2. So that's the first part. F varies jointly with the masses M1 and M2. And it varies, so also and inversely with the square, because it's not D, it's D squared, with the square of, and what does D represent? D was the distance between the objects, with the square of the distance between the objects. So basically, if the letters didn't mean anything, we could just easily say F varies jointly with M1 and M2 and inversely with the square of D. But because they've told us what those letters represent, we want to say pretty much the exact same thing, only we're actually giving names or descriptions to the actual letters. So that's why it says F, and if we really wanted to get technical, we could say the gravitational force varies jointly with the masses M1 and M2, and inversely with the square, I should have put with here, with the square of the distance between the objects. So that's kind of the idea, just to rewrite it, but using the vocabulary of variations, of combined variations. So here's an easier one for you. It's not as long. This is for the formula for the area of a trapezoid. So again, if you don't remember, H stands for height, and B1 and B2 are the bases of the trapezoid. So using that information, you want to describe the relationship as a combined variation. All right, and then our last example here is kind of putting it all together. We're giving a bunch of words. There's no formula given, so our job is to actually come up with that formula. So we're going to do that right now. So first thing I'm going to do is kind of read through the problem and give everything like some names, like some letters, so we need variables here, okay? So typically we can use the letter V for volume. So it says the volume of a regular tetrahedron varies directly, so we know we're going to have a constant, as the cube of the length of an edge. So if you want to call the length of an edge L, then it would be the cube of L, so basically L cubed. And so it's telling me that the volume varies directly, not inversely, directly, so we need a K, as the length or the cube of the length of an edge. So pretty much V equals K times L to the third power. And then they give me more information, and the information they're going to give me is going to help me solve for K. So basically what we know is that if I want to solve for K in this case, we are going to take and divide by L cubed on both sides, and K will equal V divided by L to the third power. So it says here the volume of a regular tetrahedron with edge length 3. So they're telling us that when the length is 3, so when L is 3, So I'm going to plug in here when L is 3. The volume, okay, so the volume of this tetrahedron is 9 root 2 over 4. 9 root 2 over 4. So I'm going to combine those together. Find the formula. So all I'm trying to find for now is K. Once I know what K is, then my formula is done. So I know that K is equal to V divided by L to the third power. So this, I hope didn't confuse you, but if I take 9 root 2 over 4 and divide it by 3 cubed, it's the same thing as 9 root 2 over 4 times the reciprocal of 3 cubed, which is 1 over 3 cubed, and that's why I put the 4 at the bottom times the 3 cubed. It's the exact same thing. But just in case that confused you, I didn't want that to confuse you, okay? So we know that 9 is 3 squared. So these 3 squared, you're going to cancel with 2 of the 3's down here, leaving you with only 1. So we'll get rid of that guy and just put 3 to the 1 power. So basically I'm going to get root 2 times 1 is root 2, and 4 times 3 is actually 12. So I get root 2 over 12. That's what K actually equals. So when I plug K into my formula, I will be done. So my volume is equal to root 2 over 12, that's K, and then the L to the third power is on the bottom as well. So let me go back, and that division bar is kind of weird. So why is it up there? Okay, hold on, this thing is writing weird. Okay, so volume equals, on the top we're going to put our K, on the bottom we have L cubed, but on top we have root 2, and then the 12 will be down here. So this would be your answer. V equals root 2 over 12L to the third power. That is how you do that. So you will try this guy right here, and once you have done that, you will have completed your assignment for this lesson, and I will see you in class. Thanks for watching.